This video shows the 5 basic functions in which students will see a lot in their early college math level courses. First function is linear functions. So linear functions are the functions of the form f of x equals to mx plus b, and the graph of a linear functions is a straight lines. As you see that this is the graph of a functions f of x equals to x minus 1. And in a linear functions, the constant m is called the slope of the function, and this can be found using this formula here. If you know the 2 points of a functions x1, y1, and x2, y2, the slope will be equals to the difference of y2 and y1 over the difference of x2 minus x1. And the constant b in the formula is the y-intercept. As you know that the y-intercept of the functions is a point where the graph of the function crosses the y-axis, and the x-intercept of a functions is a point where the graph crosses the x-axis. To find the y-intercepts, as a general rule, you set the value x equal to 0 and then plug it in the formula, you can find y. And in this case, if you plug x equal to 0, y should be equals to -1. In order to find the x-intercept, as a general rule, you set y equal to 0, and then you solve for x. In this case, if you plug y equal to 0, x is going to be equals to 1 as the result. The next function is quadratic functions. Quadratic functions are the functions of the form f of x equals to ax squared plus bx plus b. And the graph of quadratic functions are parabolas. And there's 2 different types of parabolas. The first parabolas is the parabolas when the value a is positive. So if the value a is positive, then you have an upward parabola. And if the value a is negative, then you have a downward parabola, as in this graph. And in quadratic functions, as you remember, we learned about the quadratic formula. And the quadratic formula is x equals to -b plus or minus square root of b squared minus 4ac divided by 2a. So why do we need to know this quadratic formula? This quadratic formula is very useful when you wanted to find the value of x if the functions f of x, the value of f of x equal to 0, which means if you need to find the x-intercept of a parabola or of a quadratic functions, then you can apply this quadratic formula here, and the x value here will be the x-intercepts of this quadratic functions. Another form of quadratic functions is of the form a times x minus h squared plus k squared, where x and h, or where h and k, is a vertex point of a parabola. What is a vertex point of a parabola? So vertex points of a parabola could be either the highest point of a parabola or the lowest point of the parabola. So if this functions is written in this form, then h and k will be the vertex coordinate of this parabola. The next function is rational functions. Rational functions are the functions of the form f of x equals to p of x divided by q of x, where p of x and q of x are 2 polynomial functions. For example, if p of x is the polynomial functions of the n degree, then it starts with the x to the n terms with the coefficients big A to a sub n. If q of x is a polynomial functions of the m degree, then it will start with the term x to the m, and usually there's a coefficients with the highest term a sub m. So these 2 functions, p of x and q of x, are polynomial functions. And we have seen polynomial functions before. For example, a linear function is a polynomial function of the first degree, of degree 1. So x to the 1 is the highest degree in this functions. That means this linear function here is a polynomial function of the first degree. Also, a quadratic function, when you see that the highest term of this function is 2 because the highest term is x squared, that means this quadratic function is a polynomial function of the second degree. So in most of rational functions, there are some special asymptotes. First, vertical asymptotes are the vertical lines in which the graph of the functions cannot cross. And then sometimes it has horizontal asymptotes. Those are the horizontal line to which the function approaches to as x goes to positive infinity or x goes to negative infinity. Here's an example of a rational functions graph. In this example, there are two vertical asymptotes. They are x equal to 2 and x equal to 6, right here. And at this, by the definition, vertical asymptotes are the line at which the function never crosses, which means x equals to 2 and x equals to 6 will make the functions undefined. In this case, the point where the function is undefined is a point that makes the value of x that makes the q of x functions equal to 0. So if 2 and 6 are the two vertical asymptotes of the functions, then when you plug 2 into the function q of x, you get 0. And you plug 6 into the function's q of x, you get also 0. Now, we have a horizontal asymptote in this graph, which is y equals to 2 is a horizontal asymptote. And you can see that the graph approaches to this line y equals to 2 at x goes to positive infinity. Also, the graph approaches to this line at x goes to negative infinity. That makes this line y equals to 2 a horizontal asymptote of this rational function. The next functions are exponential functions. So exponential functions are the function in the form f of x equals to a times b to the x. As you can see that in this case, the x, the independent variable, is the exponent of a base b. Usually, b has to be positive. And then this is the graph of an exponential function. This is the general shape of an exponential function. So you can see that it's not a straight line, it's not a linear function, it's not a parabola, but it's an increasing curve. And the last functions are logarithmic functions. And logarithmic functions are the functions that form log base b of x. So now x here is the independent variable, and f of x is the dependent variable, and b is a base of this logarithm. And the graph of a logarithmic functions is of this shape. So again, this is the shape of a logarithmic functions, and you can see that at x equals to 1, it is the x-intercept of this functions. Okay. In logarithmic functions, the functions only defines when x is positive. So the domain, the special domain of the functions is the functions exists everywhere as long as x is greater than 0. And again, 1 here is the y-intercept of the functions, because y-intercept is a point where y equals to 1 is the x-intercept of the functions. Put it here. It's a point where when you plug y equal to 0, b to the 0 equals to x. All right, so you have x-intercept, no y-intercept, and the domain of these functions is x is positive. All right. The reason why I'm showing these two functions on the same graph, it is because they are directly related to each other. For example, if y equal to log of base b of x, then you can rewrite these equations in terms of an exponential equations. So this equivalent to x equals to b to the y. So you can see that the x and y positions are interchanged from one log equation to the exponential equations. More specific examples of this equivalencies is when you have, for example, 3 equal to log 2 of 8, then this will be equivalent to 2 to the 3 equals to 8. 2 cubed equals to 8. So these two equations are equivalent. So since there's a direct relation between log and exponential functions in which the x and y value are interchanged, right? In these functions equations where y is a dependent variable, and if you convert it to the exponential functions, y becomes the independent variable. And this relations is called the inverse. So these two functions are the inverse functions of each other. And the inverse relations can be illustrated using the graph. Let's look at this graph again. This is the graph of a log function. And then if you draw a line y equals to x, you can mirror this shape, this graph, over the y equals to x line. And then you will get this shape, right? This is just the reflections of this curve over the y equals to x. And if you reflect this curve over the y equals to x line, then the new curve is a curve of the inverse functions. And in this case, this is the functions b to the x. b to the x is the functions of this graph, which is the reflections of this log functions, log b to the x over the y equals to x. So this graph illustrates the relations between exponential functions and logarithmic functions. If they use the same base, then they are the inverse of each other. All right, again, this video shows you the 5 basic functions that you see a lot in your early college math courses.